Okay, so now electric potential of a point charge. So just to recap the definition of electric potential. So electric potential at any point A is the work done by an external force, right, to move a charge, right, from a reference point, but here we are going to take infinity. So here I'm going to take infinity, right, infinity to point A, right, without changing its kinetic energy, right, without change in kinetic energy. This is the definition of electric potential, right? And let's now find that. So if I'm moving a charge, let us say this is plus Q. I have a test. And this is, by the way, this is the work done to move a unit charge, right? Sorry, unit. I should have mentioned unit charge, which means 1 coulomb. Now let's say if I take 1 coulomb charge here, right, and I move it from A to B, right? This is R. This is dr. So what's the work done? Now this Q is going to be pushing this. So if it does not, if I have to ensure it doesn't change kinetic energy, I have to move it with a constant speed. So I have to push it inside. So look at the direction of force. So my force is going to be in the inward direction, but the displacement is in this direction, right? So both are opposite. So work done by me is going to be negative. So I'll say dW external, right, is going to be force, and what is the force? Force is going to be KQ upon R square, because it's 1 coulomb. So Q1 is Q and Q2 is 1, right? Force into dr and minus, correct? So now the total. So now if I want to find the total work done from point A to point B, I'll say total. So the total work done, W, right? W is going to be integral dW, right, from initial to final point, right? And this is going to be minus integral KQ upon R square into dr, right? Now, what is my initial and final here? Here the initial is infinity and final is point A. So, my work done, right, to bring 1 coulomb charge, which is same as electric potential. So in this case, this work done is also equal to the electric potential, because I'm doing for 1 coulomb, for 1 coulomb, 1 unit charge. VA, right, is going to be integral dW, right, from infinity to A, which is going to be minus integral KQ upon R square into dr from infinity to A, and my A is at a distance R. Now just very simple integral. So my V of A, V at point A, which is a distance R, is going to be equal to minus KQ, taking it outside, minus, so it will be integral plus 1 upon R square into dr from infinity to R. What is 1 upon R square dr integral? So that this will be R to the power minus 2, so it will be minus 1 upon R, right? So it will be, so VA is going to be minus KQ, right? And the integral of this is going to be minus 1 upon R. Again, this limit should be from infinity to R, right? This minus, these two signs will cancel. So finally I'll just write in a different color. So my VA, right, is going to be plus KQ, right, upon R. This is the electric potential. Let me write it here at the top so you can see this carefully. So electric potential at point A, which is a distance R from here, V at point A, right, which is a distance R, is going to be KQ upon R. Very simple formula. Now a few things to note. This is a scalar or vector quantity? It's not a vector, it's a scalar quantity, number 1, right? Number 2, which means that, if I have multiple charges, if I was trying to find let's say there was another charge here, let's say this is plus Q, let's say there was a charge, let's say plus Q prime here, right? Then the electric field here would be the vector sum of the two electric fields, but the potentials will just add up. So it's much easier to add the potentials because it's a scalar quantity. So we'll stop here, go through all the steps, right? And after that, please take down in your notebook. Thank you.